So here in this video, what we're going to look at is something called sigma notation. Now, sigma notation is an interesting part of sequences and series, as it's essentially a shorthand way of writing out a sequence and series based on a set formula. Now, we have to be able to work with these and understand what they mean, because we'll encounter them all the time as we work through textbooks, exercises, and when it comes up to the final exam. So when I mention sigma notation, what do I mean? Well, sigma notation, as I said, it's a shorthand way of writing and calculating the sum of a series of number. So here is the definition if we were to write it out. So this here is our sigma notation, and it literally means the sum. If you look here, you've got r equals a to b, they're your limits. So this here means the sum from r equals a to b of f of r. So f of r would be whatever the function of r is, so whatever form that function takes. And it's given by f of a, so starting value, then f of a plus 1, f of a plus 2, so going up in increments of 1 from our values of r until we get to a point where we reach our upper limit here. So basically it's the sum of the function in whatever format the function is, covering all the values from a to b, including the a and the b. We start at the a, we finish at the b. And that's what I've explained right here. So the sum of the nth term is given by the format of f of r, starting value of r equal to a, end value of r equal to b, calculate values of all of the f of r's, including a and b, and then we sum the series that we generate. And that there is how we calculate that. Now, when it comes to working with these, similarly to when we work with different elements of mathematics and there's formula or properties, there's actually several properties associated with sigma notation and sums that we have to be able to do, and we also have to be able to prove. So we're going to look at these. So the first one that we're going to look at is the sum from r equals a to b of k f of r. Now here k is just some constant value times your f of r. What that equals is k times the whole sum from r equals a to b of f of r. So we can just find the sum and multiply it by k. So how do we prove that? Well, what this tells me is that k times f of r, that's given by k times my f of my starting term, which is f of a, plus k times my next term, f of a plus 1, plus k times my next term, f of a plus 2, and that's then going to continue on and on and on, all the way up to plus k times f of b, so all the way up to my final term. What you'll notice is that every single one of these terms has a common factor of k, so it's k times something. So what we can do is take out k as a common factor and write it as k times f of a plus f of a plus 1 all the way up to plus f of b. So we can take the k out as a common factor of every single term. And this part here, the f of a plus 1 all the way to plus f of b, we know is this sigma notation section here. So that then equals k times the sum from r equals a to b of f of r. Exactly what we wanted. Second property we need to know is the sum from r equals 1 to n of just the constant 1 is given by n. So if I take sum from r equals 1 to n of 1, what that simply means is I've got 1 plus 1 plus 1, and I do that all the way up to a final plus 1, but what you'll realise is that I've got the sum from r equals 1 to n, so I've got n times. So I've done 1 adding to itself n times, so I can quite simply say that that's equal to n. That one there is all about the logic. It's all about the fact that you've got n of them, you're adding them all together, it gives you that. Next property is that the sum from r equals 1 to b of f of r equals the sum from r equals 1 to a minus 1, so a is just some other value between 1 and b of f of r, plus the sum from r equals a to b of f of r. So if I take this one here, what I'm going to do is I'm going to expand it out, and I'm going to say that that's f of 1 plus f of 2, and I'm going to continue on, and then what I'm going to do is I'm going to add in a plus f of a minus 1, so some value at some point along our sequence, then plus an f of a, then plus an f of a plus 1, and what I'm then going to do is continue that all the way on until I've got plus f of b. What I can now do is if I split this here, I've essentially got two sums, and what I'm then doing is combining those two sums together to give me one overall calculation. Now this first one here goes from 1 to a minus 1, so that there is given by that. And this one here starts at a, so my lowest value, my beginning value for r is a, and my end value is b. So I know that this first part, that's the first thing, my sum from r equals 1 to a minus 1 of the f of r. My second part, I know starts at a, so it's my sum from r equals a to b of f of r. And I know to get the overall value, I'm going to add the two parts together. So we can split it up that way, it's some generic term the whole way along. Fourth property we need to know is that the sum from r equals 1 to n of the term n is equal to half n bracket n plus 1. Well, if I was to write this out, my sum from r equals 1 to n of n, what I would notice is that this essentially gives me an arithmetic series, because this would be 1 plus 2 plus 3 plus 4 all the way up to plus n. So what I've got here is I've got a series that's an arithmetic series adding up consecutive terms, so just consecutive numbers all the way up to an nth number. Now remember, for an arithmetic series, each general term takes the form un equals a plus n minus 1 times d. Now if I was to equate this to this one here, I'd know that a was equal to 1, and d, my common difference, that's also equal to 1. Now what you've got to remember is that the sum to n terms of any arithmetic series, that's given by a half n bracket 2a plus n minus 1 times d. Now I know that a is 1, I know that d is 1, so if I substitute all of that in, I get that Sn is equal to a half n brackets 2 plus n minus 1 times 1. And if I simplify this whole thing in the bracket, what I get is that the sum to n terms for this one is a half n bracket n plus 1. So there you go, I've proven this because I've got to that term there. The next one that we need to know is that the sum from r equals 1 to b of f of r plus g of r, so two functions added together at that term, is the equivalent of doing the sum from r equals 1 to b of f of r plus the sum from r equals 1 to b of g of r. This one is relatively straightforward to prove. If we just expand each of these terms here, first term would give me f of 1 plus g of 1. My second term, what that would give me is f of 2 plus g of 2. And what I could then do is if I then continue on expanding and doing this with every single term, I'd eventually end up with a final term of plus f of n plus g of n. What I can do at this point is group together all of the f terms and group together all the g terms, and I get two separate parts of a function. So if I group together all of my f of terms, I get f of 1 plus f of 2 all the way up to plus f of n. And then if I group all the g of n terms together, I get g of 1 plus g of 2 all the way up to plus g of n. So what that means is this here is the sum from r equals 1 to n of f of r. This here is the sum from r equals 1 to n of g of r. And all I've done is added the two of them together. So there you go, that shows that one. Next one is the sum from r equals 1 to n of f of r plus 1 take away the sum from r equals 1 to n of f of r is equal to f of n plus 1, take away f of 1. Now if I was to write all of these out here, this first one here, the sum from r equals 1 to n of f of r plus 1, what that would do is that would start at f of 2 plus f of 3 plus all the way up to my final two terms, which are plus f of n in this case, then plus f of n plus 1. If I was to write below that this expanded series, I would start with f of 1, I'd then get plus f of 2, plus f of 3, and that would continue all the way up to my final term, which in this case would be the plus f of n term. Now I'm subtracting these two from each other, so if I box this off like that and I do a subtraction just going down the way, I would get nothing take away f of 1, so I'd get minus f of 1 here. Every single one of these terms then would cancel out with their matching term from the second expansion, except the plus f of n plus 1. So I'd get plus f of n plus 1, which can then be turned around and written as f of n plus 1 take away f of 1. So there you go, that's me proving that property for you there as well. So this final property we have to realise is that I'm looking for the sum of r equals 1 to n of ar plus b is equal to half an bracket n plus 1 plus b times n. Well, this one here, we can use the properties from earlier and actually split that up into a couple of different sums and end up with a times the sum from r equals 1 to n of r plus b times the sum from r equals 1 to n of 1. Now using the previous properties, we know that the sum from r equals 1 to n of r is equal to a half n bracket n plus 1. So that's everything here except the a, but it's a times that. So that gives me the half a n bracket n plus 1 part of it. And then adding on the second one, and then sum from r equals 1 to n of 1, well we know that that's just equal to n. So I then get plus b times n. So I've used the previous properties in order to be able to prove this final property that we're going to work on. So we have to be able to work with all of these properties when it comes to all the sigma notation material we're going to do and working with much more complex sums and calculations. Look at the examples video. There will be a few examples in there, the kind of thing you're going to come across when you're working through textbooks and exercises and when you look at past papers and material that you will cover later.